So now what we're going to be doing is start looking at actual spectra and seeing where different functional groups show up. Now, typically you'll see this done as, here's a chart and you'll find alcohols show up here and ketones show up here. But I think it works a lot better when we do that by looking at actual spectra. So what I've done, you'll see them over the next, 25 slides or so, is to look at each functional group that we should be able to recognize in an IR spectrum. Now, you don't need to go and memorize all of these ranges. If you were taking an exam in person, I would always give you a list of these typical IR shifts. So we start here with what is probably our easiest functional group to identify, and that's an alcohol. So alcohols generally show up between about 3100 and 3500 wave numbers. In addition to that, these are generally a strong and broad peak. So when we say strong versus medium and weak, a strong peak is going to be one that comes most of the way down the spectrum. So we're talking about very low percent transmittance. A medium peak would be more in the middle, more around 50% transmittance, and then a weak peak would be one that's much smaller. We also talk about broad versus sharp. So you can see the peak that I've got outlined in red there would be an example of a broad peak. A sharp peak would be one more like this. That comes to a much sharper point. So we can see the example in this spectrum of the alcohol. Again, it's the peak that's the red box around it. It's a fairly strong peak because its transmittance is low, and we can see it's also more broad. And that's going to be true for most alcohols, but not all of them. So if we go to this spectrum, you can see in this spectrum, this is also an alcohol. And what I've done, as you'll see on each of these spectra, is the functional group in question is always going to be circled or have a red box around it. But what we see here is that peak is the alcohol peak. And what's different from the previous spectrum is that here it's much sharper. It's still a very strong peak. Why is it so much sharper? Well, this molecule has internal hydrogen bonding. And if we redraw its structure, so we're using pH to abbreviate those aromatic rings, you can see that the carbonyl here is right next to the OH group. And so we get an internal hydrogen bond between those two atoms. What that results in is a much sharper IR peak for the alcohol. All right, now also in this range above 3000, we also find another functional group, and that's the amine. So amines show up between 3100 and 3500 wave numbers as well. But we can easily differentiate between them and alcohols. How do we do that? Well, you might notice from the peak that I'm drawing your attention to here that this amine peak is much sharper, but it's also only of medium intensity. So that's the difference between an alcohol and an amine in an IR spectrum, is that the alcohol is a strong, broad peak, whereas the amine is much sharper and medium. But there's actually even more to say about the amine peak. So if you notice, this spectrum is for the compound. The compounds are always pictured down here on these slides. So what kind of amine is this? So this is a secondary amine. Does it change if we go to a primary amine? Does that look different? Well, let's look at one. So here you can see we have a primary amine. We know it's a primary amine because the nitrogen is bonded to 2 hydrogens instead of 1. Or we could say the nitrogen is bonded to 1 carbon. And you should notice an immediate difference. The primary amine will almost always give us 2 peaks. Why is that? Well, what we're seeing here if you think back to that slide where we watched the video of the different types of stretches and bends in an IR that make up IR, you may recall that there were 2 types of stretches. The symmetric stretch, where these 2 are stretching the same way at the same time, or the asymmetric stretch, where the behavior is opposite. And that's what the 2 peaks are. One peak comes from the symmetric stretch, one comes from the asymmetric stretch. But this only is happening for a primary amine. A secondary amine, because it only has one NH bond, this doesn't show up. It only shows up as 1 peak. Finally, what about a tertiary amine? So here we have an example of a tertiary amine. What do we find in that region? Well, the answer is, in that region, 3100 to 3500, there's no peaks. And the reason is the peaks that we're looking at in these spectra are the NH bond. The carbon-nitrogen bond unfortunately shows up well into the fingerprint region, so it's not a peak that we can usually rely on. So we can, in an IR spectrum, we can see primary amines, we can see secondary amines, but unfortunately tertiary amines aren't something we can really see. Now, one other piece before we continue to go on is, because sometimes students will go to this site, all of these spectra that I'm using here come from a site known as the SDBS, the Spectral Database. It's a fairly large database. It's completely free to use, and they have on this website spectra of many IR, NMR, mass spec for many common compounds. And so a lot of times in experiments, in lab, students will get their IR spectrum and they'll go to the SDBS and look up the spectrum and compare them. And what happens a lot of times is that they'll say, well, the spectra are similar, but they're not exactly the same. And one of the reasons for that is that oftentimes this is a consequence of how the spectrum was taken. So if we go back to the first spectrum we looked at, if we look up here at the top right, it says liquid film. The next spectrum says KBr disk. And then this most recent one says carbon tetrachloride solution. So that's 3 different ways of taking an IR spectrum. Does it matter which way we use? So let's keep in mind what we have here for our primary amine. We had 2 peaks at about 3480 and 3395. And recall that that was in a carbon tetrachloride solution. So we change this, take the same compound, get a spectrum, but as a liquid film. So notice the peaks have actually moved a little bit, and the spectrum, a lot of the other peaks, while they're in the same spots or pretty close, they look different shapes, etc. And so that's again our way of saying that the method that we use, the way that we take the spectrum, does have an impact on what the spectrum looks like. So what do these different things mean in terms of the techniques? So some of these are, I would hope, pretty self-explanatory. Carbon tetrachloride solution literally means the compound has been dissolved in some carbon tetrachloride and taken as a spectrum there. When it says thin film or liquid film, most commonly the way that that's done is to use what's known as a sodium chloride plate. And you can see some pictures of them here. So these are some examples of what we would call liquid, well, not liquid film, but these are the sodium chloride plates. And a couple things happen with these. So what this means that you do is often that you'll put a solution of your compound onto one side of the plate and then just let the plate sit for a minute and let the solvent evaporate, and you're left with just a film of your compound. One of the problems though is these salt plates are pretty sensitive, and as they get scratched, chipped, used over time, that can have an impact. And then you also saw some of these were referred to as KBr pellets. Well, KBr pellets are by far my least favorite way of doing an IR spectrum. In fact, I will be honest with you, I have not done a KBr pellet since probably before any of you were born. Because what a KBr pellet involves is, you can see these 3 things down here. So one of these, you screw one inside the other, and then inside there you put a small amount of your compound mixed with potassium bromide. Then there's another screw that you then screw in on top. Then you put them inside of what's known as a KBr press, and you make a pellet by increasing the pressure. The problem is, if you don't apply enough pressure, then you get a pellet that's way too thick and you don't get a spectrum. If you crank on your KBr press too much though, if you crank on the KBR press too much, you'll get a hole in your KBR pellet, and then it's also equally useless. So a lot of people don't like KBR pellets. I'm included in that crowd, and if I never run one again, I'll be perfectly content with that. Sometimes though, and in fact, we actually don't even have a KBR press here. So sometimes I do wish that we had one, because I'd love to have, just make you run one that way once, so that you get an idea of what some of these old techniques are like, and get a little more appreciation for the instrument that you get to use. And so this is a picture of one of the IR spectrometers that we have, and it has pretty much the easiest sample prep you could ever imagine or want. Why is that? Well, if you look at this silver plate here, if you're dealing with a liquid, all you do is put a couple drops of liquid on the center of that plate and take your spectrum. If you're dealing with a solid, you just put a small amount of the solid in the center, and then you tighten this down until it won't tighten anymore. And you don't even have to worry about over tightening it, because once it gets to the point where it's supposed to be, it will not go any further. And you get very, very nice spectra from this instrument. Nicer than anything I ever got with a KBR pellet. So, but that's why you might look at the same spectrum of the same compound and say, wait, why is it different each time I look at a different spectrum? Well, it shouldn't be drastically different, but there may be some subtle differences here and there. So let's move on with some of our peaks. So we're going to look at an alkyne now. And an alkyne, the way it shows up in an IR spectrum is largely dependent on what's attached to the alkyne. So this alkyne is what's known as a terminal alkyne. And that's going to look very different from our next spectrum, which is an internal alkyne. So what's the difference? An internal alkyne is an alkyne where both carbons of the alkyne are attached to additional carbons. Whereas in a terminal alkyne, one of the carbons of the alkyne is attached to a hydrogen. Terminal, we could think of the alkyne, the molecule ends at that point. So does this mean that we can actually differentiate between internal and terminal alkynes just by looking at their IR spectra? The answer is yes. So every alkyne has a peak between 2100 and 2300 wave numbers. That represents the triple bond itself. And we can see that peak here in this spectrum. In this case, you can see it's medium intensity. Now, that peak still exists for the second alkyne I've pulled out, but you can see here it's a much, much weaker peak. So overall, we say that alkynes are medium to weak. So there is some variability in their intensity, but medium to weak. And in general, they are sharp peaks. But in addition to being able to see the triple bond, if we have a terminal alkyne, the CH of a terminal alkyne is generally strong and sharp and shows up around 3,300 wave numbers. So this one, being a terminal alkyne, you can see has this strong sharp peak out here. If we go back though to our internal alkyne, you can see that in this 3,300 region, there's pretty much nothing there. Finally, to sort of close out this region above 3,000, one other thing, or in the range of 3,000, one other peak that we want to talk about. So you may have noticed, and if you haven't, you can go back and look at some of the other spectra, that pretty much every spectrum that we've looked at, plus every one that we're going to look at beyond this, has some peaks 2,900 to about 3,050. We haven't really paid attention to those. The reason for that is those are carbon-hydrogen single bonds. And if you think about what that means, every organic molecule has carbon-hydrogen single bonds. So we get a peak in that 2,900 range in just about every spectrum, and it's not terribly significant to us. Now, in that same range as alkynes, that 21 to 2,300, we also find nitriles. So nitrile is a carbon triple bonded to nitrogen. We see the example of a nitrile peak here. What usually differentiates them from alkynes is that both of them are sharp. We saw alkyne peaks were as sharp as well. But the main difference is that nitrile peaks are a little bit stronger. So most nitriles, we would say, are of approximately medium intensity, whereas alkynes are weak, getting up to medium, but usually not as strong. But that does lead us to a fairly important question. If nitriles and alkynes show up in the same region, how can we distinguish between them? Because in the first alkyne we looked at, let's go back to it, the intensity of that alkyne peak, the transmittance, was 47%. This nitrile that we have here is 49%, so almost identical. How do we tell them apart? Well, this is a good illustration of why IR alone isn't enough. And so once we would go to an NMR spectrum, whether it's a proton NMR or a carbon NMR, that will give us more information about whether we have a nitrile or a carboxylic acid. All right, so the remaining functional groups that we're going to look at will be our sp2 carbons, and that's where we'll pick up in our next video.